Dr. Arnab Dutta, or Arnab Dutta to be very honest. Because I have heard that IIT people are very, very particular. They don't want a doctor to be written because they say we know we are, and then you can write professor or whatever. So I'm very happy, and I would say I'm really honored to have Professor Arnab Dutta with us. Though Sayantan is going to officially introduce, but I have just interacted with Professor Dutta, I believe in 2 or 3 occasions, but whatever occasions I have interacted with him, I realize that there's a vast difference between how we people are as teachers in our college and how they are. And there's a huge gap. Huge gap means it's a huge gap. Maybe because we ourselves are not that much exposed to the way teaching should take place. And I was amazed the way he was describing some of the simple, complex things in very, very simple language. And I really wanted that if somehow we can invite him to our college campus, and it just happened by chance that our team had already contacted him. So when they told me that, ma'am, we have sent a mail to Professor Arnab Dutta, so I was really happy, and I was telling, no, he's an excellent person, and we should have him on our campus. So, and just now I was observing, so I observed he's Dutta, we have Nia Bose, we have Sayoni, and we have Sayantan. So they're all a gang of intellectuals. They were all chatting, so I'm sure that all of us are going to get benefited. Sayantan, you can take forward.
Okay, so I think Ashram has given a pretty good teaser, but let me go ahead with the trailer. So bear with me. Okay, so good afternoon everyone. So we are back again with Zach's very own series of guest lectures on various fields of chemistry and related disciplines, ChemCruise. Today we have with us Professor Arnab Dutta.
Okay, so thank you all, and thank you Professor Agarwal for this kind introduction. Thank you the Xavier's team for this introduction. Can you please turn off this channel a little bit? I think I cannot hear myself. Okay, so good. So it is actually a great pleasure to come to St. Xavier's College, because although in our IIT we are teaching and we are doing a research, we actually miss a little bit of this college vibe in the IITs, because everyone is studying and studying, not much fun, at least not in the colleges or the classrooms. In the hostels there is a different story, and I am actually a hostel warden, so I know some of the stories. And then I come over here today, just entered around 1:45, and I found like this is something I can relate with. I actually went back to my presidency college days, where a lot of things happens even outside the classes, and I can see this vibrant student group around. So thank you for bringing the good memories of my bachelor's life. Bachelor of Science, by the way. So that coming to here, today I'm going to talk a little bit about this recent development on molecular catalyst-driven small molecule activation. A lot of jargon words you can say, so I would like to break it down and tell you the story. What are some of the biggest challenges we are facing right nowadays, and how chemistry can hold the key to solve them down, and how we can actually learn from the biology and connect it with chemistry and find the solutions. And I would like to take a little bit of different approach. So I would like to have this session a little bit interactive. So I'll sometimes ask a question, don't worry. That will not be your final exam question. So feel free to answer. Because one of the important things first, you have to learn that you have to be curious. And also, don't worry about saying something. It may be wrong, but at the end, if you learn the right thing, that is the way to go. At the end, most important thing is what is right, what is wrong, rather than who is right, who is wrong. Okay, so first of all, we all currently living in a system or a time where energy is one of the most important factors. Right now, if I ask you, can you live without your mobile phone, smartphone or laptop? This is harsh. No, cannot. And now say that we can have your laptop or smartphone, but you cannot charge it. It is like we are living without oxygen. So right now, this energy is very important aspect to us, and we need more and more energy as the population is growing, and as we are improving our lifestyle. 30 years back, our energy consumption was much lower. Right nowadays, it is not. For example, right now I can see all these interesting gadgets are here. 10 years back, we not even think about it. So we are actually increasing our energy usage. The population is growing. Can anybody know what is the current population? Yes, so all of you are actually following the news. So we just crossed the 8 billion. So which of the countries will be requiring more and more energy? It's obvious answers, because we are going fast and we are the most populous country. So that is where we are. And believe me, those are where the geopolitical situation is actually revolving around. That is where the wars are fought. Who are going to control the energy? And now, if I say, what is the main resource where we are getting that energy? What will be your answer? Where do you get the energy from?
Coal, fossil fuels.
Fossil fuels. What are the three major fossil fuels? Coal is there. And natural gas, that you actually use the cooking gas. So natural gas, coal and petroleum. So these are the major resources. Almost 40 years back, they are the major resources, and even after we are having so much solar panels, wind panels, if you look all around the world, take an average, still more than 80% is coming from there. So what is the problem with these fossil fuels? Problem is that when we try to extract energy from it, what do we do? Basically burn. We are getting energy, but we are producing another demon with that, and that is carbon dioxide. And now see how much we actually change it all around the world. This one, you probably cannot see it pretty well, but you can see a line going back and forth like a heartbeat, and all of a sudden it goes skyrocketing. So this is the line showing how much carbon dioxide was there, and this is a timeline of time. So this is 500,000 years, and this is current time. So this dotted line over here showing that the carbon dioxide level always remained below 300 ppm over the last 500,000 years. And we human beings did something around 1970s. It skyrocketed, and today, what is the carbon dioxide level, anyone? Roughly, what is the carbon dioxide level in the atmosphere today? Will be dead by then. It is 420 ppm, close to that. So almost 140 ppm extra than what was before 1970. What happens in 1970s or 1950s? We find out that there are oils all around the place. We can dig it out, we can burn it, and we can extract energy. So that was the beginning of our modern industrialization. And over there, we skyrocketed that carbon dioxide, and then the story you know, carbon dioxide come into the atmosphere. It is a global warming or greenhouse gas. It is storing a lot of energy. Not only it is melting the ice caps and putting the polar bears in the problem, it is putting everyone in a problem. Space like Mumbai, we are very close to the sea. If it raised by another 1 meter, this will be our ground level. So we have to be careful on that, and not only that, it is also creating a problem on the balance of the climate. So what is climate? Wind flow and the flow of the things in the sea, all those things, sea wave flow, and all of them is very tightly controlled by the temperature. Temperature is one of the factors. And over there, a simple temperature change of 0.5 degree, 0.6 degree is creating a little havoc. And what we are actually heading towards, as we all know, 1.5 degrees centigrade or 2 degrees centigrade more than what it should be. And that is creating a problem. Now the thing is that, is the world is going to be destroyed? No. World can survive higher carbon dioxide than that. When the world, the earth we know, when first it created, the carbon dioxide amount was close to 95%. That was there in Mars right now or Venus right now. But over here something amazing happens known as photosynthesis. That actually converted the carbon dioxide to oxygen. We have life. So we can also survive. The earth can also survive, say like 700 ppm or even 1000 ppm of carbon dioxide. Problem is, we human beings can be extinct, and that is all we are actually worried about. We worried about ourselves first, then the environment. So we have to ensure that the environment is in such a way that it can keep ourselves in the picture. So now, first thing, we have to agree that yes, it is a problem. That is the first thing we have to agree. And it is not only us to agree, the world leaders to agree that yes, it is a problem, we have to do something. Now all of you are following the news, so COP, the Climate Change Conference, is happening almost every year. In 2015, it happened in Paris. Over there, India took the lead, and they said like, okay, it's a big problem. We are coming forward and saying that we will cut down our carbon dioxide emission by 45% in 2030, and we will be carbon neutral by 2070. And then we reiterate that in the current COPs, last year in Glasgow, this year in Egypt, which just getting finished. So that is very good. Now the question is, when we talk about carbon neutrality, can anybody say what is carbon neutrality? Anyone?
Equal amount of carbon emission and carbon absorption.
So we are actually living in a world of carbon. So that amount of carbon is constant. We cannot change it. What we can change, what is the form of that carbon. And what we don't need is carbon dioxide, and it shouldn't be in the atmosphere. They are the problem. Now over here, what we are saying that whatever the anthropogenic activities we are doing, energy harvest mostly, we are going to burn the coal, but we are not going to produce that carbon dioxide and leave it into the atmosphere. Before that, we will do something so that it doesn't see the day of the light. So that is called carbon neutrality. And when you are saying, for that we have to know actually how much carbon dioxide actually we do emit. Any idea how much carbon dioxide India emits every year? A rough number. First, what is the scale? Tons, 1,000 tons, million tons, billion tons.
Million tons?
How many of them you think is a billion ton? It's actually in billion tons. Yes, in India we are actually every year emitting almost 2.6 gigatons or 2.6 billion tons of carbon dioxide. And it is a government given number, so you know. And in the world, how much we emit every year? Rough number? In India it's 2.6. 7. Any other number? 8, 9. More? Okay, it is close to 35 billion tons at this moment. And again, we are not probably getting the full data in some of the countries. So say it is close to 40 billion tons. So 40 billion tons of carbon dioxide we are right now emitting. And this number is going to be constant or is going to be going up? Going up. More carbon dioxide, more energy, all those things are connected. In India, we are emitting 2.6 billion tons or 2.6 gigatons in 2020. In 2030, it is not going to be 2.6. It is going to be 4 or 5. So up 50% of that we are going to say cut it off, not 2.6 what we are emitting today. So that is something in mind. And 2070, if we are going to continue in the same path, we are expected to emit almost 10 to 15 billion tons by India itself. So that we have to neutralize. So it is not about neutralization, but also the scale we have to be thinking about. Now this is a problem that we have to ensure that that much huge amount of carbon dioxide can get emitted from the system. Now what is the solution for that? Solution is to first handle the carbon dioxide directly, do a carbon dioxide management. When the carbon dioxide is coming, the problem is carbon dioxide in the atmosphere, don't let it go there. Capture it and then convert it to something else or store it to a place but it doesn't come back. That is called carbon dioxide capture, utilization and storage or sequestration, CCUS. That's the term you're probably hearing a lot. That means don't allow the carbon dioxide to go, and if you're doing that, we can continue using the coal or continue using the petroleum or the natural gas, not a problem. The problem is carbon dioxide in the atmosphere. So that is one. And second thought process was, can we have an energy solution where we can get the energy at similar level as the coal, oil or natural gas, but it doesn't produce a baggage of carbon dioxide. So that is why we found renewables. So the good renewables are solar energy, everybody knows, wind energy in Maharashtra, everybody knows, we all see the wind panels, at least in the movies. So they are actually working, providing energy, and those are very good. We also have hydrothermal, we also have tidal energy and geothermal energy. All these energies are good. Now the problem is that these all energies are good, that none of them have the baggage of carbon dioxide. But the problem is they are not consistent. What do you mean by consistent? For an example, right now say some of you want to go from here to say Pune. and you want to drive a car. You exactly know how much petrol you want to have in your car depending on the mileage, and if that amount of petrol is there, you will reach to port. Because what you are actually depending on, a 1 liter of petrol, how much energy it will give, it is constant. It will be same over here, same over in US, same over in Europe. It's constant, and we can rely upon that. Similarly, when we have a kg of coal, a bucket of coal, we know exactly how much energy I can produce. I know exactly how much electricity I can produce. And that is actually the reliable energy source, consistent energy source we can get. Can we say the same thing for a solar panel? Today is a very shiny day, we can have some amount of light, but say the same day in a monsoon, we almost forget what is sunlight is. And at that point of time, it cannot produce enough solar energy to give you electricity to run the everyday work. So for an example, in this particular college, say we need 100 kilowatt hour of energy, and for that you need 3 hours of good sunlight, if it is there. If it is not there, then what do? You have to have the backup. You cannot do everyday work without having that energy. So that consistency is actually missing in this renewable energy. Same thing happens on the wind energy. You never know which direction is flowing. Is this enough speed to run the turbine? If it is flowing to a particular amount of time so that you can get that amount of energy. So those things are typically missing in these renewables. So renewables are good, but the problem is consistency. And that is something we need, because as a consumer, we always need to have that energy in my home. We don't want load sheddings, right? So that is what it is actually problematic in the renewable energy sources. Next, the question is, what is the solution for it? The solution is biology. What is the source of energy in the biology? Through photosynthesis. Sunlight. Now imagine what a tree is doing. In its leaf, it has something called chloroplast. So this is a rough picture of the chloroplast. There are particular machinery made out of proteins. In the proteins, you have some enzymes. They are actually capturing the carbon dioxide and converting it to carbohydrate, glucose. And over there, this carbon dioxide to carbohydrate. If I ask you, the chemist, what kind of reaction it is? Acid-base redox? Acid-base or redox reaction? Carbon dioxide to glucose. It's a redox reaction. You all know how to calculate the oxidation number. Carbon dioxide oxidation number is +4. In carbohydrate like say glucose, you have a CH bond. The oxidation number goes down. So that means it's a reduction reaction. Any reaction needs energy to run. Where is the energy coming from? Carbon dioxide to carbohydrate. The sunlight. Sunlight is doing the energy production, the energy transformation, and the carbohydrate is formed, the CH bond is formed. And in this bond energy, we are storing the energy of the sunlight. So that means biology depends on like transform the solar energy to a chemical energy. And now we have a glucose in the form of rice, roti, whatever. If it is storing an energy, that is also constant. It doesn't really matter whether I am eating the rice in the morning or the night, I am going to get the same energy. And nowadays we are all very cautious, so we know like 100 grams of rice give me how many calories, right? So that is the energy conversion, and that energy is actually coming from solar energy. So biology is saying store that energy in the form of a chemical bond. Once it is in a chemical bond, now it is consistent. Now you can know exactly how much energy I can convert. How to convert that? We are actually doing it right now. Whatever the lunch we have right now, it is metabolizing in our body. We are producing the ATP in our cells in mitochondria. Exactly the opposite reaction going on. Carbohydrate is getting oxidized back to carbon dioxide and it's leaving energy and it is capturing in the form of ATP. So over there it is showing that we can actually use a redox cycle, carbon dioxide to carbohydrate, and by that we can capture energy, we can release energy. So we thought like, let's replicate it. But obviously we are actually a little bit of lazy chemist, and at the same time we are not as good as the biology, because carbon dioxide to carbohydrate, it is a pretty complicated reaction. It requires a huge amount of time, huge number of steps, and as you know, organic transformation, if you are going to 10 or 12 steps, I forget all my chemistry. So we want to keep it as simple as possible. So what is the simplest reaction we can think about for forming a chemical bond? And we say this proton to hydrogen. 2 protons plus 2 electrons. It's a hydrogen molecule. And this hydrogen-hydrogen bond, I am going to store the energy. Architect or the blueprint is the same, but instead of carbon dioxide to carbohydrate, I am doing proton to hydrogen. So that is why hydrogen becomes one of the important factors nowadays, and you are reading in the papers, green hydrogen we need to save the world. That is because hydrogen can do this stuff, store the energy from the renewables and store that energy. And whenever you are requiring, you heard this term called fuel cell, where you probably at least heard this thing that Europe is running buses and trains on hydrogen. How they are running, they are not really burning them, they are using something called fuel cell, where the hydrogen energy is transforming into electricity. So we know how to extract that energy, we know how to gain that energy and forming that hydrogen-hydrogen bond. So that is the blueprint we are going to follow. We are going to store that energy in hydrogen-hydrogen bond, and hydrogen-hydrogen bond is quite a strong bond. You can gain a lot of energy out of it. Okay, look into that number. A huge amount of energy, kilojoules per kilo of hydrogen you are actually storing. So just to give a rough number, 1 kilo of hydrogen can give you 32 kilowatt hour of energy in electricity. I don't know how many of you follow your electricity bills. At least your parents are following, you can ask them. At least in my home, I know I am actually spending close to 100 kilowatt hour every month. So if I have 3 kilo of hydrogen, I am set for the month. So similarly, you can find it out. So that amount of energy you can actually store in hydrogen. So very good source. Obviously, there are some problems. You are going to come into that later. But just to give you an idea, proton to hydrogen is not the only thing you can do. You can do other combinations also. Water to oxygen, ammonia to nitrogen, carbon monoxide or methanol to carbon dioxide, and so on and so forth. It is up to you what you want to do. But proton to hydrogen is still the simplest one. So that is one we want to follow and showcase that it is doable, and then we can slowly go into the other combinations of the molecules. Now, hydrogen, where we are standing. It is not like something hydrogen we are not using. Hydrogen we are using every day in a huge amount in different fields. We don't really understand it, but it is going on. So, any guess how much hydrogen we use every year in India? Tons, 1,000 tons, million tons, billion tons? Billion tons, 1,000 tons? It's in the million tons. 5 million tons of hydrogen. We can actually use every year, we are actually consuming every year. And what is the usage of that? Mostly use it as fuel. We burn them and get a lot of energy. Second thing is chemicals and formation, like metal purification. The final stage is metal reduction. Hydrogen as a very good source of reducing agent. So we use that. Hydrogenation reactions, making daldas. As a Bengali, I'm a very good sweet lover. So we also know these reactions. So hydrogen is very important thing that we are doing. Right nowadays, we started using hydrogen for actually providing the heat in the buildings. Instead of like using coals, we are actually burning hydrogen, get heat, and running the heat through the channels all over the buildings and heat it up. So that we are doing in the cold areas. So all those things are running. We are also started doing a little bit of transportation. So this is the use of hydrogen. And if you look into this map over here, it is showing on the bottom left, bottom right corner, that what is actually the status of hydrogen usage all around the world. And you can see India is almost absent. Only one dot. That is because in Faridabad, close to New Delhi, Indian Oil has a center where they are actually producing hydrogen and running buses just for showcasing, nothing more. Recently, we also have one in Assam. We are producing 10 kilo of hydrogen per day. So that is the 2 dots we have. And right now, we believe that in the next 10 years, not only India is going to have a lot of dots, but we will be the hub of hydrogen technology all around the world. And Government of India also put a roadmap how to go forward to that. But the problem is where we are getting so much of hydrogen. As we said that we are producing hydrogen every year, 5 million tons of it. Where we are producing from? We are right now producing it from coal and steam, methane reformation. Coal we basically burn it in a closed container, in a converter, and producing hydrogen plus carbon dioxide, carbon monoxide, and all the other gases in methane also. Then we take the methane as natural gas, burn it with steam at a high pressure, high temperature. We are producing hydrogen. Again, side product is carbon dioxide. So not only you are producing hydrogen, but you are also producing a lot of carbon dioxide, which is known as the carbon footprint. So that is not the solution. That is the problem we are going to solve. So we are getting more problem. That's not the solution. But still we are doing it because they are actually cheap. 1 kilo of hydrogen, if I produce from coal or steam, it costs like 120 to 150 rupees. But if we are going to do that in a different process, they are costly. What are the different processes? Let's say we are a little bit smart and we say like we'll do that with coal and methane, but we will not allow the carbon dioxide to go outside. We will capture it and store it. CCUS technology. That we can do, but the CCUS technology needs money, so that will be costly. So this hydrogen processing, where we are actually capturing the carbon dioxide, which is known as the blue hydrogen. Blue hydrogen means it is actually captured carbon dioxide, and that cost us around 250 to 300 rupees. Now all of a sudden, if I say for the sake of environment, let's make sure that you are paying almost double the electric bill you are doing. Will you agree? Nobody agrees. So our importance is first than the environment, unfortunately. So we have to play around it and make sure that this price is competitive with the other one, and then we can talk. Just before going back, coal and steam, because they are producing a huge amount of carbon dioxide, those are known as brown or grey hydrogen. So even if you heard this term, brown hydrogen, grey hydrogen, that means they actually have a lot of carbon footprint. The other one is the green hydrogen. So green hydrogen is a process where we are going to produce the hydrogen from the proton, as we discussed earlier, as the biology is doing. So what is the most abundant source of proton in the world? Water. Yes. I'm also thirsty. So it is not only the blue. So water is the major source of proton. Who doesn't believe it? What is the pH of the natural water we are drinking?
7.
That means how much is the proton concentration? What is pH means? Minus log of H plus. 10 to the power minus 7 molar. Okay. It's a small number, but it's a number. 0.1 micromolar protons you have in this water. So if we can produce hydrogen from this little amount of protons, that will be excellent. And biology knows how to do that. So that is the process we are doing, and how we are doing it. Protons needs electrons to bind together to produce hydrogen, so we need an electron source, electricity. So that is known as water electrolysis. And if we produce hydrogen from water electrolysis, it is known as the green hydrogen production. Okay? Obviously, it is very good process, no carbon footprint, but the problem is very pricey. Right nowadays, it is costing us 500 rupees per kilo, almost 4 times than the coal-based system. So the question is, let's find out why it is costly, and can we find a solution to make it cheaper. So our goal is to make hydrogen from natural water. So now we look back, this is the reaction we are talking about, proton to hydrogen. We need to produce hydrogen from it. So just imagine if you take this water, put that in the sunlight, is it going to produce hydrogen? Because the energy is not right enough, and the molecules are also not in the right conditions. All of you have gone through the transition state, the reactant and product, delta G and all those things. So it has to create the right set of reactant and product so that it can produce the hydrogen. And for that, it needs a catalyst. So that is the catalyst we need so that we can produce hydrogen from water by shining sunlight onto it, or by putting that through electricity. So is there any catalyst available? It is there. And the best catalyst which can do that is platinum. So what is the obvious problem with platinum? We can make ornament out of it, but nothing more than that. And just imagine, we want to find a solution for all the people all around the world. So that means we need to have a widespread solution. A lot of production units out of it. We don't have that much of platinum to do that. It's not only about the affordability, we don't have that much of platinum. And that is why we have a few production units, and that is why they are very costly, because they contain platinum. So obviously it's a problem. Now what is the solution? So what do you guys do when you are in a problem, typically, at home? go to your parents, like, what is this? We do the same thing. And by scientific community, we go to our mother nature. Do you have a solution where hydrogen you are producing and you have some catalyst that you can use, some abundant matter? Obviously, they have a solution. There is an enzyme called hydrogenase. Biology is very easy, so hydrogen means hydrogen can be make or breaking, so that is the enzyme. And this hydrogenase enzyme is found in some anaerobic bacteria, which are ancient even than the photosynthetic systems. They are actually billions years old. Before the photosynthesis set in, we are actually living in a reducing atmosphere. Hydrogen was actually the system we are using for transporting energy, not carbohydrate or carbon dioxide. So at that point of time, these enzymes were evolved which contains nickel and iron in its active site. Okay, half of the problem solved. Then we look into the price. Wow, that is 1,000 or 10,000 times smaller than the platinum. So we can use it. So can we take this enzyme directly and produce hydrogen in a lot of amount? The answer is no. The reason is these enzymes are actually evolved to work in our physiological condition, in our cellular condition. In cellular condition, they only do a reaction whatever it is needed. They are not really working for some big multinational companies that they have to produce multi-tons of hydrogen every day. They only produce a few micrograms, which is good enough to run the biology or metabolism in the system. So that is the first problem, that they are actually very slow in a way, and also they are available in a very small amount. So this particular enzyme, although they contain nickel and iron and can do this reaction very well, they are available in nanograms level. And now, if you try to get the biology, overexpress the thing, and then take it out, accumulate it, go to a ton of this enzyme, you'll find that is actually more costlier than platinum. Because the biological procedures to get enough purified enzyme is very costly. So that is a problem. Second problem is, these enzymes are set to work in physiological condition. That means pH 4 to 7, 25 to 40 degrees centigrade. They are also anaerobic bacteria. Anaerobic bacteria means they are tons of scale is not the right way to do. So we hit another setback. So now the solution we try to find out over there, can we learn how biology knows how to use nickel and iron, and then we are smart enough to replicate that and develop a synthetic catalyst of our own and ensure we can produce hydrogen. So for that, we look back and do the postmortem of this enzyme. So hydrogenase enzyme come in two different flavors. One is the nickel iron, other is the iron iron. And what is the difference in the nomenclature? It says that what are the metals present in its active site. In nickel iron it is nickel and iron, over here it is iron, two irons. So that is the two iron over here which is actually doing the reaction. Now, when the catalysis is happening, what is the reaction? Two protons will come, two electrons will come, they will bind together on the catalytic active site, produce hydrogen, hydrogen goes out, next proton comes, next electron comes, the cycle goes on. To ensure that this reaction happens properly, the rate at which the electron comes to the active site, the rate at which the proton comes to the active site, it has to be very similar. And it is not that case in a reality, because electron transfer much faster than the proton. Any reason why? We also know about those terms called tunneling. Electron can just tunnel. Proton can tunnel, but not as good as the electron. So electron transfer is much faster. So if we are doing the electron transfer much faster, just imagine one set of the reactant is waiting there, where are the other set of the reaction, I am not doing the reaction. It is a mess that you don't want. So that is what the enzyme actually resolved. What they did, they make two channels. One is known as the electron channel. You guys are studying a little bit of bioinorganic chemistry? Yes? You heard about something called iron-sulfur cluster?
Yes.
No? Okay. You heard about the structure called cuban? A cube with 8 vertices?
Yeah.
Just imagine one iron in one vertex. The next vertex is actually sulfur, the opposite is iron, and so on and so forth. Okay? That creates 4 iron and 4 sulfur. That is a iron-sulfur cluster, the common one. And these are the iron-sulfur cluster over here. they are very good in transferring electrons, one electron at a time. So they have 3 different ion super clusters specifically positioned such a way that they kind of create a relay like our electricity line that transfers the electron from the bulk to the active site. That is the electron relay. So ensure electron is coming to a particular way to the active site. Second thing, you also need the proton. So how to transfer proton? So for that, you also learn a little bit about amino acids.
Yes.
What is amino acids? The building block of protein.
Protein.
Good. And in amino acids, we have some amine groups,
And
carboxylic acid groups, that's why the name amino acid. And they also have something called a side chain, which may also contain some group which can exchange proton. Alcohol group, phenol group, acid group, NH2 groups, all those things. So over there, this particular enzyme have some groups present over there which actually orient such a way their side chains are oriented for transporting proton through the bulk to the active site. And they are kind of creating a tunnel of proton ring. So just imagine in a way, you have a tunnel which actually can carry water, a pipe. Now say this pipe is totally empty. Now if you have to carry 1 drop of water from one end of the pipe to the other, what you need to do? Take the water drop and move all the way around to the pipe and then it goes on. Now imagine the same system you have to do, but now this time this water pipe is totally filled up. You cannot put one extra water molecule. Now what happens if you put one water molecule over here? One water molecule will come out. That is the same thing happening over here in the proton relay. They are totally filled up with proton. One proton comes from this side and one proton ejects over there. Because at the end it needs proton. They don't really worry about where is the proton coming from. And that is the proton relay. So this proton relay and electron relay ensures that the reaction happens such a way that the proton and electrons are coming simultaneously and synchronously. Now the question is, who is ensuring that all these things are oriented at the right direction, stationed at the right condition? So whenever we talk about an enzyme, we mostly look where the reaction is happening, the active side, the heroes and heroines of the movie. But we also have a huge support staff, and those are this protein structure. This protein structure is obviously giving the proton relay and also ensures where this electron transfer relay will be. And that creates a very dynamic system around it and ensures that the system works in a way, the way it should be working. And over here, this whole protein atmosphere, we call them outer coordination sphere. All of you know what is a coordination sphere, right? A ligand binds to the metal and controls its reactivity. It is called the primary coordination sphere because the ligand and metal are directly coordinated. Now imagine a similar group is not directly coordinated to it but still controlling its reactivity. We call them outer coordination sphere. It is not directly coordinated but still controlling its reactivity. This protein atmosphere is doing the same. It is not directly, all of them are coordinating to this ion, but still ensuring how it should behave, regulating its behavior. So this is called outer coordination sphere, and that's control the electron relay, proton relay, and sometimes also the hydrogen group. We find this is probably one of the biggest reasons why the enzymes are so good. And we want to particularly replicate that feature. But obviously we don't want to work with the enzymes for the obvious reasons. We want to make our own catalyst. We want to evolve to a new catalyst of our own where this outer coordination feature we will include it. So let's go ahead with that. This is the first complex we are going to talk about. The central metal is cobalt. Can anybody remember what is the ligand called? Just a hint, you use this ligand for gravimetric analysis of nickel. Dimethyl glycol. Use that, right? How easy is the reaction to do if you put nickel and DMG? Pretty easy. You can do it in your sleep. Same thing, you can do that with the cobalt complex also. Over here, you put 2 equivalent of DMG and 1 cobalt. It just binds to it. We start with cobalt chloride, the chloride is there, and one of the axial position, you all know what is axial and equatorial position, one of the axial position is free. If you put a pyridine over there, that creates the basic set of this cobaloxime catalyst, it's known as cobaloxime. which actually can do a little bit of hydrogen production. So good, that is a good hydrogen production catalyst, right? No, it is really not a very good hydrogen production catalyst. It's a very poor hydrogen production catalyst. So why we are considering it? Because that will be our guinea pig for the experiment. We are going to create a proton relay around it and see if we can make this one to a good catalyst. So why we chose this? As we said, it is very easy to make. You can prepare that in tons. That nickel DMT you are preparing in grams, right? In half an hour of reaction. Same thing you can do it. It can do a hydrogen production. Very poor, but it can do. So that means it has the potential to do it. Third and more important thing, it can do the hydrogen production in the presence of oxygen. That means it is oxygen tolerant. However, it cannot really do the experiment in water. Our goal is to produce hydrogen from water. So that it cannot do. So we said, okay, this is going to be a template on which we are going to test our hypothesis. So what is the hypothesis? We want to create a proton relay around it, replicating the protein. So what is proteins made of? Amino acids. So we thought we'll start with one amino acid at a time. So our goal is we'll put a tail on this pyridine and put a amino acid over there. So our goal is to prepare this complex and see if this amino acids over there improve its reactivity. Can we do the hydrogen production in water and at a very high rate? So to do that, we have to do a lot of experiments. So what we do, we create two amino acid based complexes. One is phenylalanine, I guess you all know that. It is actually phenyl group over there. And a tyrosine, which has a OH group over there. Now if we look into this closely, amino acids give you two groups which can exchange proton, amine group and carboxylic acid group. So those are there in the phenylalanine. So it has two groups which can exchange proton. In tyrosine you have another extra one, phenolic group, so three of them. Now we also created the decarboxylated version of them, like without the carboxylic acid, if we can make the complex. So this is called benzylamine, only has one nitrogen. And one is called the tyramine, doesn't have the carboxylic acid, it also has the two groups. And we also take pyridine as our control. So we prepared these five complexes. Pyridine doesn't have any group on the outer relay to exchange proton. Benzylamine has one, tyramine and phenylalanine has two, tyrosine has three. Now this is the series of the complexes we are going to look into and find if this has any effect on the hydrogen production ability of this catalyst. You are all okay up to this point? Any questions or queries? No.
I have a question.
Yes, please.
Why, out of all the other complexes, this cobalt was chosen and this DMT was chosen?
Yes, so one thing is that it is actually very poor catalyst. So whenever we are actually trying to see if there is any effect of this proton relay into this catalyst, we want to do that, say, a very poor catalyst so that any effect we can see. If we start with a moderate or good catalyst, the effect is not that important. So people might say that it's probably happening for some other reason. So what our goal, can we make a almost inactive catalyst to a very active catalyst? So then we know that this is actually happening. And secondly, this catalyst is very easy to make. So the students don't have to think too much for the preparation stage. And that is probably the main reason. So the next question is, how do we find an experiment for hydrogen production? So for that, we did an experiment called electrochemistry. All of you probably in your physical chemistry classes, you are going through electrochemistry. What is electrochemistry? You put two electrodes and do a reaction through electrodes via electrons. Because any reaction, if you look into the chemistry, we have multiple billions of reactions. But you can actually separate it out largely in two groups. One is acid-base and one is redox reaction. We are going to do a redox reaction. The electron will come from the electrode. As simple as that. So what we did, we take our complex, we put that in a solution. Solution is water, neutral water at pH 7. We put three electrodes. One is where the reaction is happening. We call them the working electrode. Now, to ensure the electron circuit is complete, we have to put another electrode where the other side of the reaction is happening. If it is happening reduction, other side will do the oxidation. If working electrode is happening the oxidation, other side will do the reduction and complete the electron cycle. And the electron will pass through, will get a current. What is current? Nothing but electron transfer. And that electrode is known as the counter electrode, where this counter electrode is. Other is known as the reference electrode because we need to know where I'm doing the reaction. And that we actually measured via potential. What is potential? E0 value. You all heard about this E0 Nernst equation?
Yes.
It's good. So it is actually connected to the Gibbs free energy or delta G. So it is actually giving a very nice example, a very nice picture where the reaction is happening. So how we actually do this experiment? We change the potential of this working electrode. And exactly where we are, we measure that with respect to the reference electrode. And then in this graph, in the x-axis, we are changing the potential. If it is a positive potential, this is the oxidation side. If it is a negative potential, it's a reduction side. So we start from the oxidation side or positive side, we slowly start moving the potential. If any reaction is happening over there, what will happen? Electron will exchange.
Yes.
If there is electron exchange, you will see a current. So this is the current. So current shows reaction happening, potential shows exactly where it is happening. So after this Electrochemistry 101, we actually start these complexes, and all of this you cannot really see it over here, but if we blow it up, we can see there's a peak over here. And this peak says there is an electron exchange. This electron exchange is happening because our cobalt complex actually exchanges one electron. Cobalt goes from cobalt 3 to cobalt 2 state. We have done other experiments to prove this is cobalt 3 to cobalt 2. And this is a very small current because that is one electron per complex. Then when you go further, you can see there's a huge change in the current. Why there's a huge change in the current? That means something is happening, it is taking multiple electrons. Not only one electron like this, which cannot even see, it's a huge number of electrons are getting exchanged. So what is happening over there? That means something is happening which is taking multiple electrons at the same time. That means you are doing catalysis. What happens in the catalysis? The same cycle goes on and on. How many times you rotate, that many electrons you are going to take. So that means this particular current is going to tell you how fast the catalysis is actually running on. And then from there we can actually calculate the rate. So the original complex, the pyridine, which is the poor catalyst, it was doing the rate of 930 per second. That means it is producing almost 1,000 molecules of hydrogen per molecule of catalyst in 1 second, which is in terms of the catalyst moderate to poor. Then when the same catalyst, same structure, only thing we are changing, putting something dangling on the pyridine. When you put the benzylamine, only one group that can exchange proton, it goes to 1830, almost doubled it. That means the proton relay is working. Is it really working? We go to the tyrabine, NH and OH group, it is almost 3 times. 2 groups giving almost 3 times, and it continued to be the same for phenylalanine. Then when we go to tyrosine, 3 groups now, the rate is almost 9,000 per second, almost 10 times increase. And what is the only thing we change? What is there on the para position of this coordinated nitrogen of the pyridine? If pyridine, there is nothing non-functionalized, but now if this huge group which contains 3 proton relay, probably exchanging proton, and that is why we are getting that such high rate. So first goal is kind of complete, that we know it is providing a huge amount of hydrogen production. That is the first step as scientist. You hypothesize something, it is showing. Now the main goal, you have to prove it, that is why it is happening. So for that, what we did this experiment right now at pH 7, that means neutral water, the water we drink. Then we did this experiment at different pHs, and we saw the same trend, that these complexes are showing that more the number of proton relay you have, higher will be the hydrogen production. Now the question is, why it is happening? Our hypothesis was, in this picture over here, tyrosine complex, to take an example, this OH group exchange electron with this carboxylate exchange with this NH exchange with this cobalaxime main frame, where there is this hydrogen bonded oxime, and there it gets protonated and the hydrogen production is happening. Very nice story, but again, as you said, you say one thing, you have to provide the proof. So what is the proof? So for that we did an NMR experiment. All of you learned about NMR. And most of the NMR study you have studied probably from the organic chemistry perspective, that carboxylic acid group comes at this position, alcohol group this position, all those things. But it also tells you very precisely what is the electronic environment around the complex in a dynamic condition. So NMR is much stronger than what you are actually thinking. And for that, we can do something called two-dimensional NMR spectroscopy. You probably are going to study that in the final year of your bachelor's or probably later on. Over there, you can find out if any particular group through the space talking to another proton, I can actually see that through an NMR spectroscopy experiment. And that particular condition is known as nuclear Overhauser effect, or NOE. Not going into the details, but over here we record the NMR two times. One in this particular scale, one in this particular scale, the same proton NMR. And over here, these are the peaks where it should come in the vertical. But if we see some cross peaks, that shows these two groups are actually exchanging protons in between in the solution. And that shows this OH group, carboxylic acid group, NH group, and this oxygen group, they are all partnering in exchanging protons. So it is supporting our hypothesis. Not only that, it also proves that water molecule is playing a huge role to ensure this is actually happening. So water is a part of this whole proton. So these groups are actually exchanging proton through the water molecule. And that is why this is becoming such a good catalyst. So just imagine, a faster catalyst means proton has to come faster. As I said, the story of the pipeline, here is your pipeline. And water and these groups are ensuring this proton relay is there. So this is a good proof, but another proof we got from the crystal structure. So over here, this is one of the complex. There is the phenolic OH group. And you can see, these are the water molecules, and 11 water molecules is very nicely oriented close to this oxygen group, and there is the proton relay in the crystal structure. So that actually provides us the suggestion, yes, you can create a proton relay and have a very good catalyst. So this thing we published and we understand that is actually happening, but we are not very happy because how we are producing the hydrogen by electricity. That means first I have to use a solar panel, solar energy to electricity, electricity to hydrogen. We want, can we really get rid of this electricity thing? Can we directly produce the hydrogen from water in presence of this such catalyst in water with direct sunlight, which is known as the photocatalytic reaction. Basically we'll shine light on this and it should produce hydrogen. To do that, we go back and we found similar cobalaxime system, but instead of pyridine, now we take something called imidazole. Why we took the imidazole? Because that is actually already reported. It's a kind of a control complex for us. This complex, if you take in this kind of a closed loop system, let's say test tube, you stopper test tube, in that you put your complex. Over there you need something called photosensitizer, which will accept the sunlight energy and give an electron out of it. That is how the photosystem works. You have to have something called photosensitizer, which will initiate an excited electron. And that electron will go to the catalyst, and the catalyst will do the reduction. Right? Instead of the electrode or electricity, now it is coming from this system when it is shined by the light. Now if it gives one electron, what will happen? It will be positively charged cation. It will not work anymore. If you want to make it work again, you have to give one electron back to it. Someone has to sacrifice an electron. And that is why you need something called a sacrificial electron donor, which is typically an amine molecule. So the sacrificial electron donor, photosensitizer, and this catalyst, these three things we put in this test tube, stoppered it and stop it, and now shine light on it. First we are doing this experiment in the lab, so we are shining a artificial light, a laser or LED light. And then we see that if any bubbles are coming out and hydrogen has very little solubility, if it is there, we will get some gas out of it and test it, an experiment called gas chromatography. You heard about that. That actually says, yes, it is hydrogen. So that we do. So that is the experiment we did, and this complex is not water soluble totally, so we have to use a 1:1 water and acetonitrile, an organic blend. And this actually produces a good amount of hydrogen in 6 hours of time. So that is good. Then our thought is that this is a good original complex. Can I design or decorate outer coordination sphere around it? So first we did these complexes, put some carboxylic acid, And then we find there is a amino acid, naturally occurring amino acid called histidine, which already have a imidazole group. So why don't we use that? So we did all these complexes, and obviously imidazole bound complex of histidine has the maximum number of proton relay, and this shows the maximum hydrogen production. So that means it also works in photolithic condition. The one important aspect we found when we put these groups, they are not only relaying the proton first, it is making the complexes totally water soluble. So that means now I can do the reaction in 100% water. So we did that in 100% water, this blue line. The first complex cannot do, it is not water soluble, but the rest of them are doing. That means a proton relay is not only improving your catalysis, but also improving your water solubility. If you are want to create a water to hydrogen production catalyst, if it is water soluble, nothing better than that. And over there we found the reactivity has gone better, more water, better than that. So that, so far we did in 100% water, in neutral water with artificial light. So what should we do next? Let's do it on sunlight. That is what the students did. They took this whole setup, instead of shining light on that, they go to the terrace, put it in the sunlight. And they did this experiment first by purging a lot of nitrogen in there, just to ensure it is stable condition, and did this experiment. And they found a huge amount of hydrogen is producing under sunlight. So natural sunlight, natural neutral water, it is producing hydrogen. However, if we want to make a very good catalyst, we should be doing this experiment in natural condition, that means aerobic condition. It shouldn't have only nitrogen, it should have air, that means 21% oxygen. We did this experiment, it is still producing hydrogen, a little bit lower. That is because this photosensitizer is breaking down. The catalyst is stable, the photosensitizer is a problem. That we can solve later on, but which shows that a system we can prepare which can work in neutral water, natural sunlight, and in aerobic condition. So you can say it is an all-weather ready catalyst. Just buy the catalyst, put it over there, put it over in the sunlight, get your hydrogen, now use it whatever you want to do. So that is what we've done, and who is actually inspiring us? The enzyme, the mother nature. So that is why we call them the enzyme-inspired catalyst design, because we are not really making the catalyst from the scratch. As Professor Agrawal just says, like, why you are using this? Because we want to show that we not always need to prepare catalyst from the scratch. We can take whatever is available and make it a better catalyst. And that is what we are actually doing. So after doing up to this point, we are preparing this outer coordination sphere. And over there, what we are using to prepare this outer coordination sphere? Amino acids. Why we are adding amino acids? Because in the nature, protein is actually creating the outer coordination sphere, and we are using amino acids. But over here, we become a little bit of swaggy and says like, okay, why you always need to follow the biology? We can make something where biology even cannot do. We will prepare an outer coordination sphere for non-amino acid molecules, but at the same time, we want to have to be cheap. So it will be abundant molecule, probably a biomolecule, and will provide us this outer coordination sphere. So which biomolecule we should use? We go back to the drawing board and figuring out that when we are creating this system, what we need. Ovaloxime is our template, that is where the reaction happening. We are not touching it at this point of time. But what we are actually doing, we are creating this imidazole or pyridine bound molecule. That means we need an N heterocyclic system. The N group is going to coordinate. And that will contain some outer coordination sphere amino acid. Our thought, can we have a biomolecule where both of them present in the same molecule? A N heterocyclic molecule which already contains some group which can exchange protons. So then we searched that and we found there are a biomolecule known as vitamins. And you all know the vitamins, vitamin B. Vitamin B has different variants. And one of the variant is vitamin B6. What is vitamin B6? It is basically this pyridinyl motif. It has this phenolic OH group, aldehyde group, and an alcoholic OH group. This aldehyde group can be exchanged with a primary amine and can be an alcoholic group. So these are the three different variants it can have. And additionally, this alcohol group can be connected with a phosphate group. So totally we have 6 different variants of that. these are, you can say, the conformers of different vitamins, so they are all called the vitamins, and all 6 of them are actually used in biology. But as I said, we are actually very lazy, so if on which of them are actually used more, that means that will be available more, I can directly use them. So the 2 we found that is used more is this pyridoxamine, this amine group 1, and this aldehyde bound phosphate group. So these 2 compounds we can easily buy, we don't have to make it, and put it with cobalaxime and prepare a set of our catalyst. Over there we also prepared this complex, which is actually control for us. And over there we found that this pyridoxamine complex, we expected that it will bind to nitrogen, but it is possibly binding through this amine group. So is it a big setback for us? Actually it is not. So while you are doing the experiments, we have some hypothesis. The compound should do this, I should get this result. But compound will do what it wants to do. What is the thermodynamics want to do? So you have to adapt to it. So first we are a little bit not very sure, like is it a good thing or not. But later on we found no matter what, a group is binding to here, and instead of amine, now the pyridine group is available for proton ring. Okay, so we'll go ahead with that and see if it is actually giving us any difference or not. But what is the proof that is the amine group is binding? So first of all, we get the crystal structure which says that amine group is bound, pyridine is not. And secondly, all of you are probably studying FTIR spectroscopy. And all of you know NH2 group has a particular staging frequency in a very high frequency region of 3300, 3400. And that band we actually got when we were looking into the free ligand. But when we put that with the cobalaxime, we found that peak is gone. That means that amine group is not available. That is connected to the cobalt. If the pyridine group was connected to there, this should be still available and you should still see a signature. So see, all these BSc studies actually come to work with this. So never think that I'm not going to use it ever. So after making these complexes, we did that again, electrochemistry, and we found all of them are really active for hydrogen production. So that means we can go beyond natural amino acid and prepare catalyst with vitamins and prepare active catalyst. After that, we find it like what are the different pHs, even at neutral pH is working good. To reduce to cobalt 1. And in cobalt 1 form, it is actually a D8 system. And it is actually have a lot of electron density. It is produced because during the electrochemistry we go to a very negative region, that potential ensures that it is getting created. At that condition, metal has so much of electron, it actually now acts as a base. So that oxime ring, which has a proton, the proton transferred to this metal. So you can say it's a cobalt 1 plus proton. And this proton takes 2 electrons from the cobalt. It becomes cobalt 3 hydride. And once it is hydride in water, it produces hydrogen, taking proton from the water. And this cobalt 3, we are doing this reaction where we should have a cobalt 1 system because we are in that thermodynamic region. So this cobalt 3 automatically takes 2 electrons, goes back to cobalt 1 again. It again takes the proton, and this cycle goes on. And we have spectroscopically doing that experiment where we did electrochemistry and one other spectroscopy, optical spectroscopy together to see one new particular feature is going, and that feature belongs to cobalt 1, cobalt 2 and hydride bound species, so that we are able to capture.
What is the percentage efficiency of your enzyme?
So I would say the efficiency of a catalyst is found by 2 different parameters. How fast it is doing, and secondly is that what is the energy efficiency, how much energy have you used. Rate wise, we are doing at this moment we have achieved up to 25,000 per second. The enzyme works around 10 to 15,000. The best reported catalyst is close to 100,000 per second. So we are, I would say, the higher level of the activity. Energy efficiency is an important factor. What is energy efficiency? Proton to hydrogen. If the reaction has to happen on its own, where the reaction should happen? Do you have any answer? Where the proton should transfer to hydrogen? At which energy? Think about the standard reduction potential. Where does the proton to hydrogen goes? Remember the standard reduction potential scale? Yes. The proton to hydrogen goes at 0 because that is how you measure. 0 versus standard hydrogen. So that is 0 at standard condition. What is standard condition? At pH 0. At pH 7, it will be 59 millivolt minus 7 because 59 millivolt it will shift. it should happen at minus 420 millimolar. We are doing this reaction at this point of time 700 to 800 millivolts. So 200 to 300 millivolts of energy we have to give extra. That is called the overpotential. That is the energy loss. So why it is lost? Because it is not that you give electron to the proton, it will produce hydrogen. The catalyst has to take the electron, catalyst has to take the proton, that does the reaction, and catalyst has to undergo different coordination geometry change. As we are discussing cobalt 322, 221, that have different geometry. For the geometry to change, you have to give energy. That is where the energy is getting lost. So if you want to minimize that energy, and if you can do that at zero energy, that is what at least where it should happen. Only two systems can do that. One is enzyme, and the other is platinum. Right now, what we are doing at 200 to 300 millivolts of energy, it is quite good, but I would say, like, why don't we try to get an enzyme which can does that almost at the equilibrium potential. So that is we are still looking for.
Do we have any more questions? Seeing none, and as much as I would want to do the vote of thanks, Sammy, the chairperson, will come in and take this opportunity. So Savani, go ahead.
Thank you so much, Arnab. So first of all, good afternoon to everyone. I feel incredibly honored to extend this vote of thanks on behalf of Xavier's Association of Chemistry. Firstly, I want to take the opportunity to express our gratitude towards our guest speaker, Professor Arnab Dutta, for very kindly accepting our humble invitation and giving us the opportunity to host this talk. I firmly believe after listening to this talk, we all have added a little more knowledge and a lot more curiosity and spark to learn about the contemporary scientific developments around the world. I'm pretty sure that the precious knowledge we have gained is definitely going to help us in the future. Once again, I would like to thank Professor Arnab Dutta for taking out the time from his immensely busy schedule and delivering this guest lecture in such a short notice. Thank you so much, sir.
Yeah, he's actually a very, very busy person.
Yeah. I would also like to thank the whole ZAC team for making this happen, and of course none of this would be possible without the constant support of Dr. Ashma Agarwal, the convener of ZAC. Himanshu sir, the secretary of ZAC, and Mr. Maraswan Kotwal, the head of the Department of Chemistry Department in Xavier's College, Mumbai. Lastly, but definitely not the least, I want to extend a big thanks to all the student and faculty members in the audience for attending this talk, and it was your support and encouragement that keeps us going every year, every time. Thank you so much, guys. With this, I'd like to extend this token of gratitude to sir, and I'd like to call Neeraj sir.
Say